Okay, welcome everyone to my continuation of what is algebraic topology. Today I would like to explain what is a hole. So what is a hole? We'll see. Or more strictly speaking, I will explain what is homology intuitively. So the whole problem a little bit with homology is that the definition um, is a little bit scary. It takes you a while to digest it. It takes me a while to write it down, and it took me a long time to digest it. I'm not even sure whether I have digested it in any way. So today is more like an informal definition, an intuitive definition, a workable definition in some sense, but not a strict definition. And the whole question is, what is a whole? So let's get started with what is a whole. So here's a topological object, which we'll see in a second again. And how many holes does it actually have? Well, certainly there's this hole, which in some sense is a how many dimensional hole? It's a one dimensional hole. But why? Not quite clear. But you can, or at least from the picture, but the point is you can kind of wrap a circle around it if you can't shrink the circle. Then you might say, okay, but there's a second one-dimensional hole which goes around like this. You also can't shrink, if you go around the swim ring, you also can't shrink the circle. So there's a second one-dimensional hole. Sure, yeah, maybe, but this is certainly harder to see, right? So is this a hole or not? Who knows? Is this a hole? What is a hole anyway? In some sense, the torus itself is a zero-dimensional hole. So this is one. And the volume in here, in some sense, is a two-dimensional hole. It prevents the torus from being shrunk to a point. So let's have a look. So here's my swim ring again. And in some sense, what I want, so this is my torus T. I'm going to the solid torus in a second, the donut, TS in my notation. I don't have a good notation for the solid torus, TS. Anyway, in some sense, a hole should be the dimension of homology. So homology should be the definition of a hole in some sense. The problem with the notion of a hole is that I'm always illustrating those nice pictures in R3, but these are not spaces that live anywhere. They're abstract spaces. In the abstract limbo, what is a hole, right? Um, Hole today is a definition, for me at least, it's the dimension of a certain homology group, or this dimension of a certain vector space. And I've written down the dimension sequence here. As I said, I would like the torus to have a zero-dimensional hole, the green one. I would like the torus to have two one-dimensional holes, the red one. And I would like to have it a two-dimensional hole, the purple one. So the purple one was the inside. It's a little bit hard to draw the inside of a swim ring. Um, there's a hole in there in some sense, right? So the one-dimensional ones were this one and this one, so going around. And the zero-dimensional one is basically the beast itself, whatever. What is zero-dimensional hole is a little bit a matter of taste anyway. With contrast, here on the right-hand side, the solid torus, it's filled, so it doesn't have any two-dimensional holes. But it's also this circle is now contractible. You can just contract it because my donut is solid inside, but this one still exists. And of course, the object still exists, so it should have one zero-dimensional hole and one one-dimensional hole. And yes, homology will spit out exactly those answers, which you can think if this is great, or actually, strictly speaking, in some sense, homology was invented such that you get those answers. So homology is a way to make precise the notion of a whole. So a zero-dimensional whole, uh, informally speaking, is a connected component. Okay. What is a zero-dimensional whole anyway? It's a matter of convention. You use that one. No convention will be intuitive anyway, so you use that one that works best in practice. And this one is the one that works best in practice. The one-dimensional is really like you could put a necklace around it, one of my circles, and that's good. So like in this picture, two necklaces, the red ones. And good picture for the two-dimensional one is it's a number of plugs you need to inflate it. Right? I don't need any plug to inflate my donut because I don't know where you buy your donuts, but I hope it's filled. But I need one plug to inflate my swim ring. So in some sense, a mathematical object has a hole if you can prevent it from shrinking to a point, right? So let's try to motivate now the definition of homology based on the idea that we want to measure holes. And the space without holes I like to consider here is a triangle that you can see here. It certainly has no holes, so it's really this filled triangle. But it will play an important role because it kind of gives us already a way to see what a hole should be. So the whole idea is based on what is called chains, cycles, and boundaries. In this case, just of triangles. So what is a chain? A chain is just an edge of my triangle. So my triangle has those vertices, it has edges, and has a face in the middle, and a chain is just one of those guys. Strictly speaking, that's not quite true. A chain should be a linear combination of edges. But anyway, let's think of this as being edges themselves. A cycle, a cycle is now anything that goes along the edges and comes back to where it started. And you think of these as being linear combinations. So there is some linearity going on. So instead of writing the cycle itself as a cycle, I write it as I go edge A, I go edge B, and I go edge C, and I denote it by A plus B plus C. There is some orientation that plays a role. For example, if I would go A and then I would go B in the opposite direction and I would go C, I would write down A minus BC. But for now, let's ignore the orientation. There's some orientation of the edges, but anyway, it doesn't really play a role. For the experts, if you like to work with Z mod 2 coefficients, it really doesn't play all of that. Anyway, so cycles, right? Cycles should pick out our holes. So cycles in those homology groups that we are trying to produce should be kind of the generators for holes. So these should be potentially interesting in whatever we do. And what kills holes is if you glue in a disk into my cycle. So if you fill the triangle, that kills holes. And these are boundaries. These are linear combinations that go around a filled triangle. In this example, both are cycles and boundaries. So A plus B plus C is a cycle and a boundary because it goes around, that's a cycle condition, and it goes around a filled space, that's a boundary condition. But on the next slide, they won't be the same anymore. So anyway, I would like to stress the strategy here. Take cycles, they go around something, they should kind of measure holes. But you don't want to take all cycles in some sense, because this cycle, for example, goes around and it doesn't create any hole. It doesn't see any hole. So you want to get rid of boundaries that are filled spaces. They go around filled spaces. So let's have a look at a slightly different example. So I take my space now, which is a triangle, which is a little missing triangle in the middle, and I took this triangulation of this triangle, very good of this whole triangle. And if you think of this edge as being A1, for example, and A2, A3, A4, then this edge is this A1 plus A2 plus A3 plus A4, because I get, this is kind of the strategy. I go along those cycles, each edge is a cycle, I just gave it names, A1, A2, A3, A4, and going along is taking the sum. Similarly here, I just gave them different names. Similarly here, I just gave them different names. And in the middle, you also have the little cycle that goes a little bit around, around the middle hole. And both of them are now honest cycles. They detect the hole, and we would like to see that in some way. And the point is, if you take now an equivalence relation on your set that you mod out by boundaries, so you mod out by those guys here, and go around, so you kill all of those, all of those cycles, you kill all cycles that go around a filled triangle, then you can actually show that these two paths are equal, which is extremely good because we only want one hole here. And we found one hole. We found many ways to go around this hole, or two ways to go around this hole. You can find many ways, of course. But both of them are equivalent if we factor out boundary. So they're congruent mod boundary. That's what I write here. Congruent mod boundary. Congruent modulo boundary, right? And the thing you use here is that you can redirect edges, and that's where this nice linearity comes in. So ABC is 0, ABC is 0, and this just means that AB is minus C. So there's a sign somewhere, but so AB is C. So you can redirect edges, right? So now you can redirect this path. So here you roughly, you go around almost around a filled area. So you can actually shortcut up to a sign. You can shortcut up to a sign, you can shortcut up to a sign, and then you successively push your way inwards. And actually you will see that those two paths, those two cycles are the same. And that's great news because now we have found a method to, well, detect the hole in the middle. You can also show that those cycles are not trivial. So you found a way to detect the hole in the middle. And this funny procedure taking everything modulo filled areas, modulo boundaries, will actually identify all ways to go around in one clockwise direction around the hole, which is really great. So the dimension of this beast will be 1. In the following slightly naive but good definition in some sense of homology. So I take some reasonable space, whatever that is, CW complexes, for example, and I take my group of chains, or in this case, I don't even want to go to abelian groups. I just want to go to vector spaces. So I take a vector space of chains, and it just has the same dimension as the number of chains. If everything is finite, let's say everything is finite, I have a reasonable space after all, right? So the dimension is this, each chain is a basis vector in my vector space. Very good. And you have this funny map delta, and this funny map delta is a so-called chain map, and it goes from CI, these are I-dimensional chains, right? So I-dimensional cells, right? So edges were one-dimensional chains. Now you can think of higher dimensional versions of those. They're one-dimensional, I-dimensional cells, and you can set the I-dimensional cells to the I-1 dimensional cells by taking the boundary. So you set everything to the boundary. I give you an explicit example in a second. And well, the kernel of this map is what you call cycles. We'll see in a second why we want to do that. The images of the map before, that's what you call boundaries. That's how they are constructed, right? Delta is the boundary of something. We'll see that in practice in a second. And what you check is that images is a subvector space of the kernel of the cycle. So boundaries, all boundaries are cycles. Not all cycles are boundaries. So what you can do is you can just take the vector space quotient and or the abelian group, doesn't really matter, and you get, well, the homology is this vector space quotient or this abelian group given by cycles modulo boundaries. Cycles modulo boundaries. How does this look in practice? So let me give you an example. So the triangle, we wanted the triangle to be trivial, right? The triangle should have no holes at all, except that it exists. So what we want is H0 is one-dimensional. Let me write down dimension. Dimension of H1 is, so how many one-dimensional holes do you see? I don't see any. How many two-dimensional holes do you see? I don't see any. So that's what we want, and that's indeed what we get. Except that I have a typo here, and this should be Q, not Z mod 2Z. Anyway, so I have some vector space Q floating around. It can be anything you want, doesn't matter in this case, just some vector space. So what are now the chains? Well, what are the zero-dimensional chains? They are the vertices of my triangle. I just gave them some names, X, Y, and Z. So C0 is just three-dimensional vector space given by basis vectors X, Y, and Z. As in my notation before, I have my A, B, C going around with a certain orientation. The orientation will play a role in a second, you will see. So this is also a three-dimensional vector space, A, B, C. And then I have a face in the middle, which I call T, like the triangle. So the two chains is just QT. And then you have those maps, which, well, you have a delta 3 map. Well, you might say now, you don't have any three-dimensional things. Yeah, the delta 3 map is just 0. And you have a delta 0 map, which goes to the 0 space. So everything is kind of flanked with maps from 0 into the first one that is interesting. And at the very end, you have a map from, so something in the middle happens. And at the very end, you again have a map to 0, kind of as a starting point. So the highest one is last non-zero one, and the other ones are 0. So you kind of can ignore those. So let's have a look at delta 2. Well, what is delta 2? Well, delta 2 takes a triangle, T, and sends it to its boundary. So it sends it to A plus B plus C. In matrix form, because this is a one-dimensional vector space, this is a three-dimensional vector space, and I've chosen the basis for both, you can actually think of this as just being the vector 1, 1, 1. Very good. So what is the map delta 1? Well, it goes from C1 to C0, so it associates to each edge its start vertex and its end vertex, just with a sign. In my notation, the end vertex gets the sign. So A, for example, is x minus y, B is y minus z, and C is z minus x. Again, this is a three-dimensional vector space. This is a three-dimensional vector space. So actually, this is a matrix. And I've just written down the matrix for you. So x, y, z, x, y, z. The image of x is x minus y. The image of y is, the image of b is, so A, B, C, X, Y, Z. The image of A is X minus Y. The image of B is Y minus Z. The image of C is Z minus X. You get this matrix. And now you're in business. You know what a kernel of a matrix is. You know what an image of a matrix is. And you just compute those. In other words, homology is nothing scary. It's just a way to associate matrices, vector spaces and matrices to a given topological object by using this philosophy of cycles and boundaries. And of course, if you would do this calculation, you get the result, the expected result with the corresponding dimensions. So the dimension is then the number of folds. Anyway, this was not so much waffle as in my usual videos, maybe not so much, but anyway, so homology intuitively is a way to rigorously define holes, because what a hole is a little bit, well, it's not really well defined, right? A hole doesn't need to live anywhere. It's defined as a dimension, or at least in this video, it was defined as a dimension of an homology group. And kind of the point is that homology groups are built from this idea of building everything basically by the skeleton of your space, the zero skeleton, the vertices, the one skeleton, the edges, the two skeletons, the faces, and so on, in a precise way that you take cycles and boundaries. And all of that sounds very scary, but actually secretly it's just a good notation for there are certain matrices and there are certain vector spaces. So this is definitely computable because they're just matrices and vector spaces. In the end, you do linear algebra. You take images, you need to compute images and kernels of matrices. Anyway, I hope homology is not too scary or doesn't sound too scary. I also hope you enjoyed the video, and I also hope to see you next time.